Next up, we're going to talk about electron configurations of ions. Now, we've talked about ions in previous chapters, but just to review, we said that cations are positive. Remember, that's how we think of it. Cat is in the word cation. Okay, it's positive. You can also think of it as it has a T, which is a plus sign, so it's positive. Okay, so they have a positive charge, which means they have more protons than electrons. So electrons were lost or removed. Okay, so certain elements prefer to lose electrons and become cations. This would specifically be all of our metals, most of our metals, so groups 1 and 2, and our transition metals, so we have to remember that. And if it's a metal, it's going to create a cation. They would rather lose their electrons, so they have a low ionization energy. They will happily remove electrons in order to form cations. Next we have anions, which is a negative ion. So this is where we have more electrons than protons. So electrons were added. Okay, and again, certain elements would prefer to gain electrons and become anions, and this is more typically our nonmetals. So that would be our nonmetals in groups 5A, 6A, and 7A. I'm using my A notation there. So groups 5A, 6A, 7A, or 15, 16, and 17. They prefer to form anions, so they have a really high electron affinity. They'd want to take on those electrons. Okay, so let's do some review. Let's remember how to count up all of our protons and electrons when we're given an element and its charge. So our first example here is calcium 2+. So the 2+ means that I have 2 more protons than electrons. Okay, so we have to remember that when we're determining our charge, it equals the number of protons minus the number of electrons, and whatever sign comes out tells us if it's a positive or negative charge. Okay, now the number of protons is never going to change. When we're forming ions, we're only varying our number of electrons, because if we change our number of protons, we change our element. So in order to find how many protons calcium has, well, we just have to look at the periodic table. So pull out your periodic table, look for calcium, see where it is on the periodic table, and that will tell you the number of protons. Calcium is element number 20, meaning it has 20 protons. And if calcium 2+ has 2 more protons than electrons, that means our number of electrons is 18. We can plug that in. We have 2+ is equal to 20 minus our number of electrons. Subtract off 20 from 2, and we get electrons is equal to 18. Okay, so our number of electrons is 18. That leaves us with a 2+ charge. Our next example is oxygen 2-, which means we have 2 more electrons than protons. So oxygen 2-, let's find it on our periodic tables so we can find our number of protons. Oxygen is element number 8, so it has 8 protons. And if the 2- charge means I have 2 more electrons than protons, that means I have 10 electrons. And if we do our math, we can do 8 minus 10 is equal to -2, which is our charge. Okay, so always double check your charges, making sure that you've noted how much protons and electrons each of those ions has. Okay. For these next 3 problems or 3 examples, what I want you to do is pause the video, go through these 3 elements, ions that I have, determine their number of protons, find them on the periodic table, and then using what we just did with our first two problems, determine how many electrons they have. Let's start off with nickel. Nickel 2+. So we have nickel on our periodic table is element number 28. So it has 28 protons. If it has a 2+ charge, that means it has 2 more protons than electrons. So that would mean our number of electrons is 26. Next up, we have selenium, Se, selenium 2-. If we find selenium on our periodic table, it is element number 34, so it has 34 electrons, or protons. And if we have a 2- charge on that selenium, that means we have 2 more electrons than protons, so we would have 36 electrons in our selenium ion. Finally, we have iron, iron 3+. If we find iron on our periodic table, we would find that it is element number 26, so it has 26 protons. And with a 3+ charge, that means I have 3 more protons than electrons, so I'm going to subtract that 3 from my protons and get 23 electrons. Okay, so now that we've reviewed how electrons are being added or removed to determine our ions, let's apply that to our electron configurations, because as we learned in our previous lesson, electron configurations tell us where those electrons are, how they're organized in the atom. So if I'm removing those electrons, I'm not just removing them from any orbital, I'm removing them from specific orbitals. So to write the electron configuration of an ion formed by a main group element, we first want to write the configuration for the atom, and I'm going to add a note there that it should be the neutral atom. So as you find it on the periodic table. Then you're going to take that configuration and either add or remove the appropriate number of electrons from the outermost shell. So that's going to be our highest N, or you can think of it as our valence shell. We're either adding or removing electrons from our valence shell. Okay, so let's look at sodium. Sodium is in group 1, and it prefers to create an ion with a 1+ charge because it has 1 valence electron. So our valence electron in sodium is the 3s1. The 3s1, okay? So if we're creating a sodium 1+, that means I'm removing an electron. So that 1 electron that's going to be removed is coming from the valence shell, or the highest N value. So it would be the 3s1. So our sodium ion is then 1s2, 2s2, 2p6. That shows us that we have now 10 electrons. In sodium, there are 11 protons. So in total, I have a 1+ charge, which corresponds to my 1+ charge of sodium there. So we've removed an electron to create a cation. Okay, let's look at an anion. Let's look at chlorine. Chlorine is 1s2, 2s2, 2p6, 3s2, 3p5, and we're creating a chlorine 1- ion, so we've added 1 electron to form an anion. Okay, so it's a negative ion. We have a negative charge on there. So that 1 electron is going to be added to our outermost shell and specifically to our p orbitals, because if we look at it, change colors, if we look at our 3s and 3p, I have 3s 2, 3p 5, 1, 2, 3, 4, 5, the one electron that we're going to add only has one place to go, and it's going to go right in that p orbital. And that's so that we can have that filled p orbital shell, because a hole filled shell makes our elements happy. Okay, so our ion configuration now has that 3p6 there, so we have a total of, let's see, 18 electrons. Chlorine has 17 protons, so if we subtract those, we get a 1 minus charge, which relates to our 1 minus charge on chlorine. Okay, so when we're writing out electron configurations of an ion, we first want to write the configuration of the neutral atom and then determine where the electrons are either going to be added or removed from. Specifically, they're going to be added or removed from the highest N value or the valence shell, wherever you think of those are the same thing. So wherever you think of, however you think of that. Okay, so it's coming from the highest N or the valence shell. Okay, so species with identical electron configurations to the noble gas to the right of them are considered isoelectronic. So if we look at sodium, which when we had Na plus, we had 1s2, 2s2, 2p6. That has 10 electrons. Now let's look at our periodic table. What other element also has 10 electrons? Well, neon does. Neon has 10 electrons, and it has an electron configuration of 1s2, 2s2, 2p6. So, because these have the same electron configuration, they are considered isoelectronic. They have the same number of electrons in the same electron configuration, because electrons are just, numbers that we add in. So if they have the same number of electrons, they have the same electron configuration. So they are isoelectronic. Now, if we look at these monoatomic ions, so here's, carbon 4 minus, nitrogen 3 minus, oxygen 2 minus, fluorine 1 minus. These all have the same electron configuration as neon, because if I have carbon 4 minus, that means I've added 4 electrons, so I have 1s2, 2s2, 2p6 now, because I've added 4 extra electrons to my p orbital of carbon. The same goes for nitrogen, as well as oxygen and fluorine. They all have the same electron configuration of neon. The same goes for phosphorus, sulfur, and chlorine. They all have the same electron configuration of argon when these are in their ionic form. And the same goes for the cations. You just have to work backwards. Okay, so isoelectronic means that they have the same number of electrons, whether they're in an ion or in their neutral form. So let's practice some of these. Let's write the electron configurations for the following ions and then determine which other element they are isoelectronic with. So we have nitrogen 3 minus. So our first step is to write the electron configuration of nitrogen. You may find it useful to pull out your diagram for writing electron configurations, the one with the arrows. I don't have it here because by starting this lesson, you should have already mastered writing regular electron configurations and completing your ALEKS homework. So I am under the assumption that you have a good grip on that, but if you do not, that's totally fine. We are still learning, so feel free to pull out that diagram and utilize that as we go through these problems. So let's look at nitrogen 3 minus. So we're going to first draw out our electron configuration of nitrogen, which is 1s2, 2s2, 2p3. And what we're going to do, so this is our neutral nitrogen. We're going to now add our 3 minus charge, meaning we are adding 3 3 electrons. So those 3 electrons are going to be added to our highest n value and to our orbital that still has space, which is going to be our p orbital. So our electron configuration becomes 1s2, 2s2, 2p6. Okay, so because we added those 3 electrons, they went into the p, and now we have a 2p6 there. That means we have a total of 10 electrons. So what other element on our periodic table also has 10 electrons? Well, that was neon. So it is isoelectronic with neon. Let's try barium 2+ next. So barium is element 56. So it may be easier to draw this as the electron configuration as a noble gas core. So we don't have to draw all of them out because we know those core electrons are not going to be removed. So our noble gas core for barium is xenon 6s2. Now the 2+ tells us that we are removing 2 electrons. So those 2 electrons are coming from that 6s shell. So we're left with just xenon. So this is still isoelectronic with xenon. So it has the same number of electrons as xenon. Let's try this again with beryllium. Feel free to pause the video and try this one on your own, and try the next one as well on your own, just to see if you're getting a handle on it, and then check your work with what I'm doing. Beryllium is element number 4, so we only have 4 electrons. So we have 1s2, 2s2. If it's a 2+, we are removing 2 electrons because we're going to have more protons than electrons, so electrons need to be removed. So that leaves us with 1s2. Those electrons that are being removed are coming from the 2s orbital, and those are the 2 electrons that we are removing in total. So we're left with a electron configuration for Be2+ as 1s2. So that has a total of 2 electrons. What other element on our periodic table also has 2 electrons? Well, that would be helium, or He. He. And if you'll notice, our isoelectronics are always going to be noble gases. Because when we're creating ions, we always want to move towards a noble gas core, because noble gases are the most stable. Okay, our last example is bromine 1-. I'm going to write bromine as argon 4s2, 3d10, 4p5. Okay, just so I don't have to write out all of the electron configuration, but if you want to write out the full electron configuration, you're more than welcome to do that. If you're still practicing how to do the noble gas core, that's totally fine. Feel free to pause your video, write out the full electron configuration, find the noble gas core, and just double check that your starting electron configuration is the same as mine. And if we're doing Br-, that means we're adding an electron, because the minus tells us that we have more electrons than protons, so we have to add electrons on. So this then becomes argon 4s2, 3d10, 4p6. So we added that extra electron to the 4p5 because that p orbitals there have one unpaired electron, so that extra electron went in and filled that space to have a full filled p orbital, which makes us happy. And this now has a total of 36 electrons, which is isoelectronic with krypton. Again, another one of our noble gases. Now, I want to make a very important comment about the d block ion configurations, because this is where I typically see students get confused or get these specific electron configurations wrong. Okay, so the ions of d block elements are formed by removing electrons first from the shell of the highest n value. Okay, so the comment that I want to make is we have to remember that valence electrons in d block elements, which is our transition metals, so those center metals on our periodic table, the valence electrons in d block come from the s and the d. And if you remember from our previous lesson, that's where we start to have the changes in our n value. So we went from 4s to 3d or 5s to 4d because they're close in energy. Okay, so they switch on us. So we have to remember that when we are forming ions for d block elements, we remove electrons from the highest n value first. So that would be the 4s, the 5s, the 6s. It's always going to come from the s first because those s orbitals have the higher n value. So take from s first, because those have the highest n value. So let's look at the example of iron. Iron is able to form an iron 2+ ion. So it loses 2 electrons, and those electrons are lost from the 4s subshell, not the 3d, because 4s has a higher n value. So if we look at, here's iron neutral, argon 4s2, 3d6. When I remove my 2 electrons, those electrons are going to be removed from the 4s first because this is the highest n value. 4 is higher than 3. So our electron configuration for iron 2+ then becomes argon 3d6. Okay, so because 3 is lower in n, okay, then the electrons aren't taken from there. Another way to think about this is, if we think about our atom here, okay, I'm going to add another layer to this image. Here's n equals 4. So in iron, I have 2 electrons in the n equals 4. Okay, that's our 4s2 electrons there. Okay, and that corresponds to here. Our 3d6 corresponds to this layer in here. Okay, the only way that I'm able to remove electrons is from the outermost layer first. It's like an onion. You gotta peel off the top layers first before you get into the middle. Okay, so if I want to remove those electrons, I first have to remove the electrons from the 4 before I can even get to the 3. Okay, so this is where thinking of the atom as these layers with shells surrounding it is easier to think of than what we're seeing in our ordering of our electron configurations. So you just have to remember highest n first, and then we go from there. Because these are shells, we have a shell that has the electrons in it. So the highest n is our outermost shell. So we have to take from that shell first. Okay. Now, iron can also form a 3+ ion. So if we look at iron by itself, it's neutral. It's argon 4s2, 3d6. If I'm removing now 3 electrons, 2 of the electrons are coming from the 4s, and then that's going away. And then that 1 extra electron is now coming from the d. So now that I've removed that outermost n, okay, so here's my 4, I'm going to draw it in a quarter-way over there. Now that I've removed the electrons from the 4, I can now access the 3 to start taking away electrons from. Okay, so once you get rid of the electrons from the highest n, then you go to the next highest n, which would then be 3. So our final electron configuration for iron is then argon 3d5. So this still shows that we have 23 electrons, but iron has 26 electrons, so we have a 3 plus charge. Okay, so always take from the highest n, and if you have to then change from one n to another, that's totally fine as long as you're going in order, because you have to think of these as shells. Like an onion, you have to peel away the top of the onion before you get to the next layer. Okay, so think of it like that. So let's practice a few of these for our D block elements. So we have zinc 2+. So zinc has a electron configuration of argon 4s2 3d10. And if I want to remove 2 electrons to create a 2+ charge, those 2 electrons are going to come from the 4s. Okay, I'm removing from the 4s. So I'm going to be left with argon 3d10, because I just essentially got rid of that entire s orbital. I got rid of the 4 shell in general. It's not even there anymore, so it just goes away. We just get rid of it. Next up we have manganese, Mn 2+. So manganese is argon 4s2 3d5. And again, we're removing 2 electrons. Those 2 electrons are going to come from the 4s, so I'm really just getting rid of the 4s, and I'm left with the 3d. Now if I wanted to make it manganese 3+, I would then subtract off another electron. That electron would come from here, so I would be left with argon 3d4. Okay, so let's try our last example. This is chromium 3+, and chromium is one of our exceptions, one of our electron configuration exceptions. So take a second and see if you can remember how to write the electron configuration for chromium based on what we've talked about for exceptions in our previous lessons. For chromium, our electron configuration in our neutral form is chromium 4s1 3d5. This is where we've moved an electron from the 4s up to the d. Oops, that's not enough. So that we have 2 half-filled orbitals. Okay. Now our rule still applies when we're creating an ion for this. So we're still going to remove 3 electrons, and our first electron is going to come from, our highest n, so we're going to remove that 4s, but that only removed 1 electron, so our next 2 electrons are going to come from the 3d. So we are going to be left with argon 3d3, because we've essentially taken these, we've removed those electrons. We've gotten rid of that 4s, and we've changed that 5 now to a 3. So we only have 3 electrons left in our d orbital, so it becomes argon 3d3. Okay. Let's do some more practice. Before I jump in and we work through these together, what I want you to do is pause the video and write out the electron configurations for each of these elements, and then try to determine their electron configurations for their ions. So first start with your neutral element, and then determine where the electrons either need to be removed from or added to. how does this affect the radius when we're creating ions, when we're adding and removing electrons? How does this affect the radius of our atom? Well, we talked about atomic radius before, and we said it depends on the number of layers, the number of shells that we have, n values. As we increase the n value, we increase the atomic radius. But now that we're changing those number of electrons, and for some of these removing entire shells, how does that affect the radius? Well, the ionic radius is the radius of a cation or an anion. When an atom loses an electron to become a cation, so if we're creating a cation, so we're looking specifically at this portion of our periodic table in our image here. So all of our metals, group 1 and 2, as well as some in 3A, when we're forming a cation, the radius decreases because we're taking away one of those shells, one of those orbits. Okay, so here I have sodium. Here it is in its neutral form, so it has all of its electrons. When I remove its electron, it's one electron, and create its ion, you're essentially just getting rid of that entire shell. You're removing it, so its radius decreases. Okay, so when we create cations, the radius is going to decrease due to a reduction in our electron-electron repulsions. And there we see that significant decrease when all of the valence electrons are removed and we're left with just the core, which is what this image was showing. Okay, so in our image up here, we see one side, this is our neutral side, and then this is our ion side. As we go from neutral to ion, that radii significantly changes because we're just removing an entire orbit of that element. Now, the trend in the radius still is that, lithium's radius is still going to be smaller than sodium's and potassium's because they just have more layers. They have more core layers themselves, or core shells, which is fine. But we have to think about how the ionic radius is going to change as I remove the electrons. Now, when an atom gains one or more electrons and becomes an anion, so we're making an anion, so we're looking at our non-metals over here, groups 15, 16, and 17, or 5A, 6A, and 7A. The radius is going to increase because we're increasing our electron-electron repulsions. We're putting electrons into that outermost shell, and they're repelling each other more because they don't like each other. Okay, so we see here, again, we have our neutral side and our ionic side. The neutral side, the neutral radius is smaller than the ionic radius. So it's the opposite of what we were just seeing with the cation. As we add more electrons, our radius is going to increase. Now, the trend, again, is still the same as we go down, that the ionic radius is going to increase as we go down a period, just because of those core electrons. There's just more core shells in those elements. But again, what we're focusing on is how the radius changes as we go from neutral to ion, and where those electrons are going and how many we're adding. So that's the end of our lesson, and overall our end of lessons in Chapter 4. Chapter 4 had a lot of focus on periodic trends and mainly electron configurations. Where are we housing those electrons? How do those electrons affect the trends in our periodic table? Okay, so this chapter was all about electrons. Before you move on to your next chapter, please make sure that you are completing your ALEKS homework and your test for this chapter, and make sure that you are mastering these electron configurations, where those valence electrons are, understanding how to remove and add electrons to create ions, because we will be utilizing that in our future chapters to build on this topic in order to create molecules.